So before we continue with the other loop types, functional types, we first discuss a few important concepts. First, we have scope and variable lifetime. A local variable is only valid in the code block it resides on. The validity of a local variable within a code block is called its scope. We also say that the local variable has a lifetime only up to when it gets out of the scope. Variables are just locations in memory. When a variable goes out of scope, the memory allocated to it in the block is freed for use for other processes. In this example, the I inside the block, this I, is not the same as the I outside the for block. Okay, as we can see, the value of I inside the block, the for loop, okay, increases while the value outside remains the same. Okay, this one. So since the loops we learned so far are essentially code blocks, we need to know, something, that the variables created inside the loop lose its scope when the loop ends. Okay, this is the reason why while loops and do while loops are not recommended to do iteration, as the iterator has to be declared outside the loop's code block. That means the iterator memory allocation is not released when it gets out of scope, leaving us with extra variable that we may or may not be able to use. Okay. Next, we say that loops rely on conditions and limit in order to terminate. A well-designed loop should terminate gracefully when the terminating conditions are met. But this is not always the case. Infinite loop. The situation wherein the terminating condition can never be satisfied and therefore the loop cannot terminate is called an infinite loop. In an infinite loop, the loop goes on and on until your program crashes. This is very bad for your program. For example, in this example, the condition, let's highlight it, this condition can never be met because I takes on only odd numbers. It starts with 1, increment by 2, 3, increment by 2, 5, increment by 2, 7, increment by 2, 9, and then increment by 2, 11. So this condition can never be met. So this body to print I will not finish. It will goes on and on. Luckily, in the compiler that I'm using, it is an online compiler. It only prints me up to 5,999 and stops. But this is not always the case when in a real program. It may goes on for a lot longer than 5,999, and it will crash your program if not your system. But there's some use for infinite loop. However, we must know how to exit the infinite loop, which we shall discuss on the next slide. There's a way to prematurely halt the execution of any loop while whether infinite or not infinite loop. This is through the use of break and continue statements. Break statement halts the execution of all statements inside the loop after the break and terminates the loop completely. Break is also used to handle cases in a switch statement, but that is outside the scope of this presentation. Continue statement holds the execution of all statements inside the loop after the continue statement and returns to the start of the loop. That means in the case of continue, the loop does not terminate but start over again to the next iteration. So let's have an example of that. In this example, the do-while loop is potentially infinite loop. This is because the condition while true is always true. It can never be changed, it cannot be falsified. So this whole loop, the whole do-while loop can never be satisfied, and this can potentially be an infinite loop. However, because we have this condition, okay, that if I equals 15, it will break. It starts with 0, increase all the time, and if it reaches 15, it breaks, okay? So this is no more an infinite loop because it will go from 1 to 15 and then stops. Also, there is a condition to continue. 5, when it is equal to 5, and when it is equals to 12, it holds temporarily and go back to the do loop. So as we can see in the output, it goes only up to 15, even though this is potentially infinite. And also, there is no value for 5 and 12 because those are skipped by the continue statement. Okay? Now we go to nested loops. Nested loops are loops inside another loop. So that is quite simple. Okay? For example, this program prints the first 100 natural numbers. 10 numbers in each line. Okay? 10 numbers in each line. The outer loop, okay, commands to do the inner loop 10 times. Okay. First we check the inner loop. The inner loop prints 10 numbers to the screen, this inner loop. And the outer loop commands it to print 10 numbers on the screen and then print it 10 times, okay? Making the therefore, okay, we need to be careful in using nested loops as the number of steps is compounded by the number of loops. So in this case, this is 10 times 10, so now there are 100 steps. Imagine having 10 nested loops for having 100 steps each, so that would be 10 raised to the 100 steps. Our program would have already crashed before the loop finishes in that case. Nested loop is one of the reasons why a program is slow. The number of nested loops should be minimalized. The ability to be nested indefinitely is one of the reasons why looping is not present in most functional programming languages. It can be, but for the most part, functional programming does not use loop or minimize the use of loops. Another reason why loops are frowned upon in functional programming community is that it is able to have side effects. Side effects is the ability of the code block to modify some states outside the scope. We can see this in our previous example of while and do-while loops, wherein the iterators are defined outside the loop and modified inside the loop. But imperative for loops can also affect other states, or imperative loops in general can affect not only the iterator, but it can also affect other state. In this example, we define the variable x we define the variable x, this x over here, and we also define a pointer to x. Okay, this variable here, not that one here. Okay. We print the value of x and p, and we can see that clearly that p does points to x. Okay, it's a pointer. Now we go to the loop. The while loop is able to modify not only x, okay, it decrements x, but also it can change the pointer. Okay, our iterator is x, so naturally it should iterate x, but it can also change the pointer, assigning it to null pointer. Null pointer means if we assign a pointer to a null pointer, it's basically deleting it. It's not deleting it, it's still in memory, but the effect is like deleting it. So when we try to print p again, we get this segmentation fault. Okay, we repeat the printing, okay, but we get this segmentation fault. Now x value is 5 and p is an error, so we were not able to print this part, the happy ending. Okay, we are faced with segmentation fault error, terminates the program and preventing us to run this happy ending. This is just a simple example, and it is easy to spot the bug. Most of the times the solution is to declare local versions of variables so we don't accidentally modify variables outside the scope. We already saw that in our example of scope and variable lifetimes, but what if we have long convoluted nested loops? Debugging can be tedious. This is the reason why in the functional programming paradigm side effects are not allowed. The ability to have side effects, infinite loops, and convoluted nest loops are the reason why most functional programming languages don't have loops constructs. Instead, recursion is encouraged. We shall discuss about recursion when we go to the topic of functions.